In this video, I want to talk about the idea of Taylor series. And Taylor series are a particular type of power series which are very powerful. Our goal here is to come up with a series, a power series, that approximates, in some sense, most functions f of x. So let's start by saying we can do this, that f of x can be expressed as some sort of power series. We looked at a few in the previous lecture. So we have some coefficient times x minus a, wherever we want to center our power series at, to the power I. And a lot of times the a is 0, so you might see something like this instead, ci x to the I. So maybe we want to center it at a different point a here, so we'll have x minus a rather than x minus 0 in some sense here. But the same ideas apply. And again, just like power series that we looked at previously, they only make sense within the radius of convergence. So that's for all x, where x minus a is within that radius r. So if we can do this, let's see if we can figure out what these coefficients are. Remember, we're saying that we do indeed know this function, and we want to express it as a power series here. So if we know the function, we can plug values into this function. And maybe a nice easy value to plug in to get our first coefficient would be to make all of these terms 0. The only thing that wouldn't be 0 is this first term, since there's no variable in the first term and there is in the other term. So if we plug in a, so let's plug in a here, what do we get? We get the sum as I goes from 0 to infinity of ci times a minus a to the I. And if we think about that, all of these terms that have an x minus a, they all become 0. So this is, I can rewrite this as c0 plus the sum as I goes from 1 to infinity of ci times a minus a, which is 0. And the reason I took that c0 out is because I'd have some number to the power of 0, which really doesn't exist here. So I'm looking at that first term separately here. But anyway, my whole point is we have coefficients times 0. So all of these guys just go away. And we have, indeed, our first coefficient. So we have that f of a equals, this should be c0 equals c0. Great, we have one coefficient now. So let's see if we can find the other ones. Now, if we can think of a way of kind of getting rid of this constant term, then we can do the same idea. And thinking, if f is a nice function where the derivative exists, well, we could just take the derivative, and the derivative of this term would go away. So that's what we're going to do. So from the last slide, we know what the first coefficient, c0, is. We just plug in that center. We plug in a. And again, if a was 0, if this was just c1x, c2x squared, then we'd plug in 0. A is 0 here. So if that first derivative exists, let's take it, and let's use that same idea that we did on the last slide. So this c0 term goes away when we take the derivative. If we take the derivative of c1 x minus a, this just becomes c1 times x minus a to the 0, which is 1, so I can just write it as c1. I am going to write it, indeed, as 1 times c1, and we'll see why in a second. So that's that one up there. So when I take the derivative, I get 1 times c1. And I can do that kind of same thing here. I'll just do these two terms here. So we're going to get 2c2 times x minus a to the 1 and 3c3 times x minus a squared. And we can keep going. All right, great. So let's play that same game. Let's plug in a. So if I plug in a into my derivative, well, I get 1 times c1 plus these other terms, but they go away since I have a minus a, since I'm plugging in x equals a. All of these become 0. So I'm going to have 2c2 times 0 plus 3c3 times 0 plus a bunch of other terms that'll all become 0. So this becomes 1 times c1. So that's great. So I've solved for c1 now. And I'm going to write it like this. It's going to look a little ridiculous, but it won't when we look for c2. So I'm going to write c1 as the derivative at a divided by 1. So that's great. Now we have the coefficients c0 and c1. So let's do the same thing for c2. So if the second derivative exists, then I already have the first, or the function and the first derivative written down, so we can use those to calculate the second derivative here. So it's going to be, this term is going to go away when I take the derivative of the derivative, or the second derivative. So I'm going to have 2 times c2 times x minus a to the 0, and I'm going to write that as 2 times 1. So this is going to be 2 times 1 times c2 to the x minus a to the 0, plus 3 times 2 times c3 times x minus a, plus, and I'll do one more term, so it's not written here, but it's in these dot dot dots. The next term would be the c4 term, so it'll be 4 times 3 times c4 to the x minus a squared, and then we have a bunch of other terms. So let's play that same game. If I plug in a, all of these guys go, and I'm just left with this guy. So the second derivative at a is going to be 2 times 1 times c2, and I'm going to rearrange that to solve for c2. So c2 is going to be the second derivative at a over 2 times 1, which I'm going to write as the second derivative at a times 2 factorial. Since I have 1 times 2, that is 2 factorial. So that's great. I have an expression for c0, c1, and c2. And in fact, I can view 1 as just 1 factorial. Why not? So you can start to see the pattern of what's going on here. If I solve for c3, I would take the third derivative, provided it exists, and this term would go away. I would take the derivative of this term. I would get 3 times 2 times 1, which is 3 factorial, times c3. This guy would go away. And all of these, if I plugged in a, would be 0. So similarly, I get that c3 would be the third derivative at a over 3 factorial. And this pattern would continue to happen as long as your derivatives indeed exist. So let's write this up on the next slide in completion. So from our previous work, we know that the ith coefficient here is just the ith derivative at a divided by I factorial. And that's as long as this ith derivative exists. So putting it all together, remember we had that original function f of x. Well, we could write this as, we wrote it as ci times x minus a to the I, as I went from 0 to infinity. But we just solved for what ci is in terms of derivatives and factorials. So let's put that in. I equals 0 to infinity of fi of a over I factorial, that's our ci, times x minus a to the I, and that's as long as f of x is infinitely differentiable. And remember, this holds for all x such that, or let's write it like this, x such that x is within the radius of convergence. So this is our radius of convergence. So that's awesome. We've, in some sense, come up with a way of writing any function, as long as we can take the derivative infinitely many times, in terms of an infinite polynomial. This one is centered at a. If you wanted it centered at 0, you just let a equals 0. And in fact, that case is very important. So let me write that down. In fact, maybe first I'll say this is called the Taylor series of f of x. And this is centered, should say the Taylor series centered at a. And the second note is if a equals 0, this is usually called a Maclaurin series. It comes up so much since it's really easy to deal with. It has its own name, the Maclaurin series. So that's great. As long as we have a bunch of derivatives of a function hanging around, a function can be as complicated as we like, and we can write it as an infinite polynomial, which is really, really excellent, because polynomials are a lot easier to deal with than complicated functions a lot of the time. So this is a very, very powerful technique here. We'll talk about this a little later, but I do want to point out that to develop this, we kind of assumed that f of x had a power series representation. However, not every function has a power series representation. There are some pathological weirdo functions out there where this kind of idea won't work. And we'll talk about that a little bit later on. But for the most part, any functions that you'll deal with in real life, not all of them, but most of them, you can indeed apply this idea. So a good thing to do is to see if something we know has a power series representation, 1 over 1 minus x, for example. That's kind of our simplest example. To see if this makes sense, if this jives with our new technique. So we need our derivatives here to be able to do this, so let's just calculate a bunch of derivatives. So I'll write the function as the 0th derivative. We know that's 1 over 1 minus x. And let's also plug in 0. We want a Maclaurin series. We want this centered at 0. We're thinking of these guys here. as x minus 0, and this would be x minus 0 squared. So our a in this case is 0. This is a Maclaurin series. So let's plug in 0 into this function, and we get 1 over 1 minus 0, which is 1. Okay, that's great. The first derivative you can check just by using, say, the quotient rule. Is 1 over 1 minus x squared. And if we plug in 0 into that, well, we get the exact same thing. We get 1 over 1 minus 0 squared, which is still 1. That's great. Let's do the second derivative. So again, you can check this just by using either the quotient rule, or it might be easier to think of this as 1 minus x to the negative 2. And if you do that, you find that you're going to get, and I'm going to write it as 1 times 2 over 1 minus x cubed. And the whole idea is I'm looking for a pattern that's happening, a general form for the nth derivative. So I don't want to kind of simplify things until I notice that pattern. So I just want to write this as I multiplied 1 times 2. And if I plug in 0 here into the second derivative, I indeed get 1 times 2 over 1 minus 0 cubed, which is still 1 times 2, which, as you'll notice, is 2 factorial. Let's do the third derivative. And again, you can check this using the same method as before. This is going to be 1 times 2 times 3 over 1 minus x to the fourth. And if we plug in 0 into the third derivative, we get 1 times 2 times 3 over 1 minus 0 to the fourth, which is indeed 1 times 2 times 3, which is 3 factorial. So, in general, the nth derivative, or let's say the ith derivative, since I'm using I as the index here, the ith derivative, it looks like it's going to be, well, here we have the second derivative is 1 times 2, the third derivative is 1 times 2 times 3, and it should be pretty easy to see that the ith derivative, the same pattern is going to hold, 1 times 2 all the way to times I over 1 minus x to the 1 more than I plus 1. And if I evaluate the ith derivative at 0, I get I factorial over 1 minus 0 to the I plus 1. So I factorial over 1, which is just indeed I factorial. So I have my ith derivative here. So I can use the idea of a Maclaurin series or a Taylor series centered at a equals 0. So I have that 1 over 1 minus x is going to be the sum as I goes from 0 to infinity of, remember, it's the ith derivative centered at a, and in this case a is 0, over I factorial, that's our ci, times x minus a, so x minus 0, which is just x, to the power I. So we can fill all this in. This is going to be the sum as I goes from 0 to infinity of, and let's make sure that this formula jives with the early derivatives. Well, is 0 factorial 1? It is indeed. In fact, it is defined to be 1. So we're fine. This is 0 factorial. 1 factorial is 1. So we look good to go here. So for all of these, this is going to be I factorial over I factorial times x to the I. And the I factorials cancel. And we're just left with x to the I, which is indeed 1 plus x squared, which is exactly what we had looking at it as a geometric series. So this method works for a function that we know. That's great. So let's do something that we haven't seen before. Let's do e to the x. Now this is a nice one because the derivative of e to the x is e to the x, so our life becomes very easy here. So we know that the ith derivative of e to the x is still e to the x. That's great. And it's a Maclaurin series, so we want to center it at 0. So the ith derivative at 0 is going to be e to the 0 for every derivative, which is indeed 1. So we know all our coefficients, all our ci's, are 1. So we can say that our function e to the x is going to be the sum as I goes from 0 to infinity of our ith derivative at our centers, in this case our ith derivative at 0, which is 1, over I factorial times x minus 0, or just x to the I. So we have a nice power series representation for e to the x now. So this becomes, I'll just write it out the first few terms, 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the 3 over 3 factorial, and we can continue like that. So we've turned e to the x, this exponential function, into a infinite polynomial function with these nice, let's say, factorial coefficients. Okay, so let's find the radius. For what values x can we use this for? So since this is a power series, let's use the ratio test to help us find this. So let's divide the n plus 1th term by the nth term. So this is going to be, the I plus 1th term is going to be x the I plus 1 over I plus 1 factorial. And I'm going to multiply by the reciprocal, which is like dividing. So this is going to be I factorial over x to the I. Okay, and let's cancel as much as we can here. So all of these x's go with all but one of the x's above, and the numbers 1 times 2 times 3 all the way to times I get canceled with everything but I plus 1 in the denominator there. And if you're not sure of why that's the case, maybe write it out with a little more detail and you should see what's canceling here. So this becomes x is left in the numerator, and the only thing left in the denominator is I plus 1. All right. Oh, actually, I changed the indices here. I wrote them as n and then I, so I'll change these to i's since I had the index label as I. And let's take the limit as I goes to infinity of our term here. So x over I plus 1. And remember, the x is constant in this. It does not have anything to do with the I there, so we can take that out. So the limit as I goes to infinity of 1 over I plus 1, which is indeed x times, and you can see that this limit here, as I gets big, this denominator gets big, so this number goes to 0. So we have x times 0, which is, of course, 0 for any x, which is always less than 1. Remember, when we're ever doing the ratio test, we know our series is going to converge when the ratio is less than 1. Or I should say the limit of the ratio is less than 1. And this holds for all x. No matter what x is here, I'm going to get 0. So this has an infinite radius. So r is indeed infinity. This is always less than 1. So the series works for all x in the real numbers. So that is fantastic. We have indeed a nice infinite polynomial that basically is e to the x, and this works since the radius of convergence is infinity. This works for all real numbers x. That is really, really fantastic. So, a good question is, well, when can we actually do this? So I want to talk about this just in a little bit of detail, not in too much detail. But if you remember from our previous discussion on the previous slides here, that we kind of assumed that f of x had a power series representation. But that doesn't necessarily always hold. So let's see what has to happen in order for this to make sense. So I'm going to define the partial sum here of our Taylor series as big T of n of x, big T n of x here. And as n gets bigger and bigger, in fact, as n goes to infinity, then we get our Taylor series. So as n goes to infinity, we get our Taylor series, our infinite sum. Great. So I'm going to make a little definition. I'm going to define the difference between our function and the nth Taylor polynomial, this is called. Maybe I'll make a note here. This is the nth Taylor polynomial. So I'm going to call that difference r of n. I'm thinking of this r of n like the remainder. And in fact, I can write that. I can rearrange this formula for the Taylor polynomial. So it's the function minus kind of how much we missed by. So minus the remainder. Okay. So remember, this limit as n goes to infinity of our Taylor polynomials, this is our Taylor series. This is that infinite sum that we want. Well, when is this actually the function that we started with? Well, let's do some algebra here. So I know that t of n, well, that's the same thing as f of x minus this nth remainder. So let me swap out t of n with f of x minus the nth remainder. And I'll split up into two limits here. So I have the limit of some function that's fixed as n goes to infinity. The function is just going to be the function. It has nothing to do with n. So the limit is just the thing itself. So it's f of x minus this remainder term as n goes to infinity. But I want this to actually just equal f of x. So I want this guy to go to 0. I want this limit to indeed be 0. And so, kind of the criteria here. So Taylor series exist. When this Rn of x goes to 0 as n goes to infinity. So I'll just briefly talk about an inequality that's out there that gets you a little bit of a handle on our n of x. It's called Taylor's inequality, and we'll talk about that in the next slide. So I just want to show you this. We won't do too much calculation with it, but we can bound the remainder kind of the same way we bounded our approximate integration back in that chapter. It has the same type of a formula here. So we know it can be at biggest m over n plus 1 factorial times x minus a to the n plus 1, where m is kind of a bound for the n plus 1th derivative for all x within some sort of radius d here. We won't do too much work with Taylor's inequality, but know that you can use this to show that the remainder goes to 0 as n grows. This is a very good technique in order to do that. And for those of you interested, an example where a Taylor series doesn't exist is f of x is e to the 1 over x. So I won't work out the details, but try this one if you're curious to see what's going on there.